Hello guys, welcome back into mathematical lesson. We are still continuing with the riders, the circle Euclidean geometry. Now we will be doing this question 12 right here in front of us on the screen. Now, we are going to have a look first on 12.1. Like I said, that we are going to prove the tan chord theorem. So now the statement that I'm having here seems to be blurry. Now I think the better option is to also rewrite it here so that you can see it. It says use the diagram below. Use the diagram below to prove the theorem that which states that angle EFG is equals to angle FDE or EDF. EDF. Now, use the diagram below to prove the theorem which states that the angle EFG, I'm sorry, which is this one, the angle between tangent and the chord, is equal to that angle EGF right there. Now, this is the tan chord theorem. So, in order for you to prove the tan chord theorem, you are given the center there. You will have to construct the diameter. So the diameter passes through the center. It goes there. Now, this diameter that we have drawn, you join it with that angle there that forms this tan chord of ours, right? Yeah, like that. Now, what are we going to do now? We know that this is the diameter. Now we need to have a letter here, maybe a letter A. So you'll be having this diagram on your answer sheet. You will just have to draw the construction FA, which is the diameter, and you join the letters DE. Now, we know that AF is the diameter, is perpendicular to FG, reason being the radius is perpendicular to the tangent, right? So, which is a statement and the reasoning. Now, let us go to the next part. So, this, since we have the perpendicularity, this is 90 degrees. We also have another 90 degrees there. Okay, let me write this one. So AFG is equals to 90 degrees because of the perpendicularity. Now, ADF, this angle here, this one, right, is equals to 90 degrees. Why? It is an angle subtended by this diameter. Angle subtended by the diameter, by the diameter, or angle in a semicircle. Angle in the semicircle. Right, fine. Now, what you are going to do, you are going to let this angle to be x. You will write it there on your diagram, on your answer sheet, that this angle here is x, right? Now, if this angle here is x, okay, you say let EFA to be x. If this angle is x, that angle will also be x because we can see our bow tie shape. This is the bow tie shape. So this angle is equal to that angle. So angle ADF is also equals to x. Also have x there. Why? Because those are the angles in the same segment. Or the angles subtended by the same chord, or the angles subtended by the same arc, right? Now, what angle are we looking for? EFG. EFG is equals to, we said the whole angle is 90 degrees, but now EFG would be 90 degrees minus x. 90 degrees minus x. Okay, let us go there. We want this part. We said that whole one is 90 degrees. So this angle will be 90 degrees minus that x. Now the angle EDF is also equals to 90 degrees minus x. Now therefore EFG is equals to EDF. Why? Because these angles, oh, what is happening? I'm sorry for that. Because they are both equals to 90 degrees minus x. Then we're done answering 12.2. Now we can just go to the next one, which is 12.2. They are saying to us in the diagram below, BOC is the diameter of this circle. AP is the tangent to this circle at the point A, and AE is equals to, okay, we can see here AE is equals to EC. Now, we can go for the technique DRCPT. The diameter, this is the diameter. Now that diameter subtends this 90 degrees angle here. Okay, there are the radius. This is the radius, that is the radius. OA is equals to OC. Therefore, C1 is equals to A2 here, right? And this one is a radius. This is also the radius. B is equals to A3 there. Okay, we also have 90 degrees here. Why? Because this radius is perpendicular to that tangent. Okay, then the cyclic chord, it looks like we don't have any cyclic chord here. Then the P parallel lines, you don't have any parallel line to the tangent you have in the tangent. This angle is equals to that angle tan chord theorem. Okay, now let us quickly go to into the problems and see what we are required to do now. In 12.2.1, we are required to prove that BA, which is this one, is parallel to OD. How are we going to prove that this is parallel to that? We can, in order for us to prove the parallel lines, we either have to use the corresponding angles, the converse of corresponding angles, or the converse of the alternating angles, or the converse of co-interior angles. So look, the first thing that we are going to do here is the theorem 1. This is the line drawn from the center. It goes all the way to this chord and it bisects this chord. Why? Because we were told that AE is equals to EC. Therefore, if it bisects the chord, it forces these angles to be 90 degrees, right? Now, you will say E2, but an angle, not just the letter E2. An angle E2 is equals to 90 degrees. Now, since this is a Euclidean geometry, you need to provide some valid mathematical reasoning behind this statement. Why do we say E2 angle E2 is equals to 90 degrees? It is because of the bisector that is drawn from the center to the chord, the converse of theorem 1, right? Now, the next one, we are having BAC, angle BAC is equals to 90 degrees. BAC is equals to 90 degrees angle in a semicircle or angle subtended by the diameter. Now, therefore, BA is parallel to OD. We have 90 degrees, we have 90 degrees. That is the converse of the corresponding angles. You are done. You have your beautiful 4 marks inside the pocket. Now, the next one, 12.2.2, we are required to prove that AOCD, it is a cyclic quadrilateral. If we draw a circle here, that will become a cyclic quad. Now, what are the properties of a cyclic quad? Opposite angle of a cyclic quad are supplementary angles in the same segment, or exterior angle is equal to interior opposite angle. So now, let us have a look on how we can do this one. How can we maybe prove that this angle is equal to that angle, or this one is equal to that one, or this one is equal to that one, or this one is equal to this one, or now this one is equal to that one, or this one is equal to that one, or now we use the opposite one and show that if they are supplementary. Then now, by doing that, we will be proving that this is a cyclic quad. Okay, now what can we do? These lines are parallel. If these lines are parallel, this angle is equal to this angle. This angle is equal to this angle. Oh, lovely. Now, you can just say angle B is equal to angle O1. This and this, they form my F here. That is the corresponding angles. Corresponding angles are always equal. Why? Because BA is parallel to OD, right? Yes. Now, angle B is equals to this B is equals to that A1 there is equals to angle A1. That is the term called theorem, right? Now, A1 is equals to O1. Why? Because they are both equal to B. They are both equals to angle B. Therefore, now these angles, since they are equal, AOCD is a cyclic quad. That is the converse of angles in the same segment. In the same seg. Okay, we go to the next one, 12.2.3. DC is a tangent to circle at C. DC is it? Oh, DC is also tangent. I now see it. And then now, oh, well, we have to prove that. We have to prove that. So we maybe can use the tan chord theorem that this is an angle between the tangent and the chord. Therefore, that will be equal to the angle that is opposite the chord, which is this one. How can we show that? Now, this angle is equal to that angle. We need to show that. Oh, let me have a look on how we can prove that one now. Okay, this is the radius. We can go there. A minute, guys. Still trying to figure this one out. How can I show that this angle is equal to that one? Okay. Okay, it is going to be here as well, because this other radii. Now, when it is here, oh, there we go. There we go. If we let O1 maybe to be x, if we let this angle to be x here, and then AOC will be what? AOC. Will it be 2x? This will be x as well. Okay, yes. This will be x as well. If this is x, why will this be x? Because this will be x. Okay, let me rephrase that. I said to you, when I let this angle to be x, this angle will also be x. Why? Because, look, these lines are parallel, right? Now, these angles are equal. Now, this is angle at the circumference. What will angle at the center be? It will be 2 times x. So the whole of this angle is 2x. We already have x here, meaning also this one will be x. Okay, let us go with that one. We said let O1 to be x. Therefore, angle B is equals to angle O1. They are both equals to x. What is the reason here? Corresponding angles, because BA is parallel to OD, right? Then now, sorry, O2 plus O1 is equals to 2x. Angle at the center is 2 times angle at the circumference. Now, also O2 will be x. Okay, you understand that part. Now, what will C2 be? Will C2 be equals to O2? C2 and O2, because we have proved that this is a circle and that will be a cyclic quad. Therefore, now C2 here will be equals to O2. This angle will be equals to that angle. Now, we're saying C2 is equals to O2. Angles in the same segment. Now, we have proved that this is also X. Now, how does a tan chord work? This is an X, that is an X. Since we will say, oh, where will I write this one? I will say, since B, which is this one, is equals to C2, then DC is a tangent at C. That is the converse of a tan chord theorem. Otherwise, let us end here for this one, guys. Now we will meet in the next one, whereby we will be continuing with these riders. Thank you, guys.